Hello, greetings to everyone and welcome to this video lecture on cosmology. Today we are dealing with the theme of mechanistic cosmology, the mechanistic universe. Mechanistic cosmology is an interpretation of the universe which coincides with the conception of the universe presupposed by Newton science. It is also called classical cosmology or classical physics. Mechanism considers the universe as a giant machine which runs automatically according to fixed laws. Let us see the pioneers of mechanistic conception of the universe. The pioneers of the mechanistic conception are Francis Bacon, Nicolaus Copernicus, Galileo Galilei, Johannes Kepler, and Isaac Newton. And let us see first little bit about Francis Bacon. Francis Bacon is known for his work in inductive method. According to him, the organon logic of Aristotle, on which all ancient knowledge was based, was not a proper method to acquire knowledge. Aristotelian method only systematizes the existing knowledge. It does not help us to acquire fresh knowledge. According to him, therefore, we must start anew and rebuild science. This ambitious enterprise is called Instauratio Magna, the Great Restoration. For this project of great restoration, there should be a new method, a novum organon, which is the inductive method. To attain genuine knowledge, according to him, we must combine the sensitive and rational faculties. Hence, according to Francis Bacon, we must ascend in an orderly and methodical way from experience to propositions of higher generality until we finally come to the most general axioms and principles. Inductive method helps us to reach the uniform laws of nature. These laws are reached through the three stages of the inductive process, namely the table of presence, the table of absence, and the table of degrees. This is how Francis Bacon proposes his new organon, the new method called the inductive method of doing science. Now let us come to the next pioneer of the mechanistic conception of the universe, Nicolaus Copernicus. He lived from 1473 to 1543. He was a Polish astronomer who challenged the geocentric view of Ptolemy. Ptolemy, a great astronomer living in 100 AD in Alexandria, propounded geocentric theory. According to geocentric theory, the Earth is the center of the universe, and Sun and the planets revolve around the Earth. This theory reigned supreme for 1400 years. And Copernicus overthrew geocentric theory of Ptolemy and proposed heliocentric theory. According to his theory called the heliocentric theory, the Sun is the center of the universe and the Earth is a planet revolving around the Sun. He gave a detailed description of this theory in his book De Revolutionibus Orbium Celestium, on the revolutions of heavenly spheres, written in 1543. Heliocentric theory propounded by Copernicus was supported by Galileo, Kepler, and Newton and other modern astronomers. Thus, Copernicus became the pioneer of modern astronomy, and his theory heralded a new era in the development of astronomy. Now we come to Johannes Kepler. Johannes Kepler lived from 1571 to 1630, he was a German astronomer. He was another pioneer of modern astronomy. He presented his theories in his book New Astronomy, written in 1609. Kepler worked as an assistant of Tycho Brahe, a Danish astronomer at the Royal Observatory in Prague. He held the Copernican theory even though his own master Brahe supported geocentric theory. He used the observations of Brahe but rejected geocentric theory. He enunciated his own laws of planetary motions known as Kepler's laws of planetary motions. The three laws are the following. First, the law of elliptical orbits. The path of a planet is an elliptical orbit with the sun at one of its foci. The second law is the law of areas. That is to say, the radius vector drawn from the sun to a planet sweeps out equal areas in equal intervals of time. The third law of Kepler is harmonic law. That is, the square of period of revolution of the planet around the sun is directly proportional to the cube of semi-major axis of elliptic orbits around the sun at the focus. Now we come to Galileo Galilei. He is the father of modern science. He lived in Pisa, Italy between 1564 and 1642. His important work is Dialogue concerning two chief world systems, Ptolemaic and Copernican. Galileo rejected the Aristotelian doctrine that the rate of fall of bodies depends on their mass and density. On the basis of experimental evidence, he established that all bodies fall to the earth at the same rate of acceleration, irrespective of their mass and density, if we neglect the effect of air resistance. Galileo conducted the experiment of dropping a cannon, that is of the big gun, and a musket ball, that is handgun, from the leaning tower of Pisa, and found that both reached the ground simultaneously, contrary to the teaching of Aristotle. Galileo was the first to understand the concept of inertia, that a body at rest remains at rest and a body in uniform motion continues its motion unless it is compelled to change that state by an external force. Newton's first law of motion originated from Galileo's concept of inertia. Galileo was the first scientist to use telescope to observe astronomical objects. He discovered that moon is not a perfect sphere and consists of mountains and valleys, and also that Jupiter has satellites. He developed Galilean telescope, which he used to observe many stars that could not be seen with the naked eye. Galileo was a staunch supporter of the heliocentric theory of Copernicus. He devoted his life to the development of physics and astronomy, and he is rightly called the pioneer of experimental method in physics. Next, we come to the famous scientist of the mechanistic theory, Isaac Newton. Isaac Newton is one of the greatest scientists. He lived in England between 1642 and 1727. He was born in the year Galileo died. Newton was a great theoretical physicist and a gifted mathematician. His most important work is Philosophiae Naturalis Principia Mathematica, written in 1687. Newton is the founder of the classical physics. as we know it today. It is he who explained the concepts of inertia and force and formulated the three laws of motion. Inertia is the property of matter by which every body preserves its state of rest or of uniform motion in a straight line unless it is acted upon by an external force. Force is that which changes or tries to change the state of rest or of uniform motion of a body in a straight line. So we see the Newton's three laws of motion. It can be stated as follows. The first law of motion. Every body continues in its state of rest or of uniform motion in a straight line unless it is acted upon by an external force. This is called the law of inertia. The second law states that the change of motion is proportional to the force impressed and takes place in the direction of the force. The third law states, to every action there is an equal and opposite reaction. Newton propounded the corpuscular theory of light, which describes light as streams of particles emanating from the source of light. He showed that white light consists of 7 colors and explained the formation of rainbow. It is Newton who discovered the existence of gravitational force between all bodies in the universe and the law of universal gravitation, and Newton is very famous for this law of gravitation. Many apparently diverse phenomena such as the free fall of bodies to the earth, the motions of the moon and the sun, the ocean tides, etc. are manifestations of one and the same law of nature, the law of universal gravitation that he states in his theory of gravitation. According to this law of gravitation, there is a force of mutual attraction between all bodies of the universe, be they grains of sand, stones, planets, or stars. The presence of universal gravitation explains the stability of the solar system and the motions of planets and other celestial bodies. According to the law of universal gravitation, the gravitational force exerted by a body is proportional to its mass. This means that the more massive a body is, the greater its gravitational force. Moreover, the gravitational force is inversely proportional to the square of distance between two bodies. This means that the farther the bodies are, the lesser their gravitational force. The gravitational law is stated as follows. Every body in the universe attracts every other body with a force which is directly proportional to the product of masses and inversely proportional to the square of the distance between them. Even after the development of Einstein's theory of relativity, Newtonian mechanics still holds good for motions with a speed slower compared to the velocity of light. Newton may be called the father of classical physics for his great contributions to the development of physics and astronomy. Now, having seen the pioneers of mechanistic universe, now let us see what is the mechanistic conception of the universe through its basic categories. The categories of mechanistic cosmology is to be explained each one by one. And in today's lecture, we take the particularly of the main categories of the mechanistic universe, the category of matter. So mechanistic cosmology is an interpretation of the universe which is presupposed by Newton's science. It is also called classical cosmology. Mechanism considers the universe as a giant machine which runs automatically according to fixed laws. The categories or most important concept of mechanistic cosmology are matter, motion, space, and time. These are thought to be absolutely independent of each other. So we take matter. According to mechanistic cosmology, matter is independent and absolute. Matter is the common name for all material particles. Material bodies are thought to be composed of small atomic solid particles. Atoms are the simple units out of which all things in the universe are made. Matter is defined as full space. This means that matter is a reality which occupies certain portions of space. Material particles cannot have the qualities of particular material bodies, which are the combinations of atoms. Occupying space is the essence of matter. A number of physical attributes of matter can be derived from this definition. That is, if a matter is full space, then material particles must be impenetrable, indivisible, indestructible. The impenetrability of matter follows necessarily from its definition of matter as full space. That is, if matter is full space, it cannot be penetrated. That is to say, what is full cannot be simultaneously filled by something else. Hence, material bodies are therefore impenetrable. Now, indivisibility of material particles too follows from the definition of matter as full space. This is one of the cornerstones of the atomic theory. The observed divisibility of material bodies does not contradict it. Material bodies of our experience are the combinations of atomic particles, and so they can be divided with instruments. But atoms or material particles themselves cannot be divided. This indivisibility of matter cannot be compared to any kind of hardness, for instance, that of iron or diamond. The hardness of such substances is not infinite so that they can be divided, provided there are sufficiently powerful instruments. But the hardness of atoms is infinite so that it is indivisible. Since atoms are indivisible, they are also indestructible. A positive term for indestructibility is constancy or permanence. This means that atomic particles are constant in their mass, volume, and shape. The constancy of matter is stated by the principle of the conservation of matter. That is, the total atomic masses in the universe remain constant. Now, having explained now the prime category of the mechanistic conception of the universe, the matter, we just make mention of a different explanation of the universe by the new science with the quantum theory. Quantum theory explains the matter in a different way than the mechanistic conception of matter, which is a basic fact that is constitutive of the universe. Quantum theory or a quantum mechanics, as it is also called, was formulated during the first 3 decades of 20th century by an international group of physicists including Max Planck, Albert Einstein, Niels Bohr, Louis de Broglie, Erwin Schrödinger, Wolfgang Pauli, Werner Heisenberg, and Paul Dirac, and many others are also included in that. From their conception of the material particles or studying their observations and studies of subatomic particles of matter gives a new idea of the world. Let us see what is that by way of something different from that of the mechanistic conception of the universe. Quantum theory stems from the experimental investigation of atoms at the beginning of the century. Far from being the hard, solid particles of time-honored theory of the mechanistic universe, atoms turned out to consist of vast regions of space in which extremely small particles, the electrons, that moved around the nucleus. Some physicists assert that every atom is more than 99.999% empty space, and the subatomic particles moving at a lightning speed, though this space through this space actually are bundles of vibrating energy. In fact, after some years of research, quantum theory made it clear that even the subatomic particles, the electrons and also the protons and neutrons in the nucleus were nothing like the solid objects of classical physics. These subatomic units of matter are very abstract entities which have a dual aspect. Depending on how we look at them, they appear sometimes as particles, sometimes as waves. And this dual nature is also exhibited by light, which can take the form of electromagnetic waves or particles. The particles of light were first called quanta by Einstein. Hence the origin of the term quantum theory that comes from his calling the particles of light as quanta, and now they are known as photons. This dual nature of matter and light is very strange, that is particle wave nature. It seems impossible to accept that something can be at the same time a particle, an entity confined to a very small volume, and a wave which is spread out over a large region of space. And yet this is exactly what physicists had to accept. It's a very strange observation, strange finding with regard to the subatomic particles. The situation seemed hopelessly paradoxical until it was realized that the terms particle and wave refer to classical concepts which are not fully adequate to describe atomic phenomena. An electron is neither a particle nor a wave, but it may show particle-like aspects in some situations and wave-like aspects in others. While it acts like a particle, it is capable of developing its wave nature at the expense of its particle nature, and vice versa, thus undergoing to particles. This means that neither the electron nor any other atomic object has any intrinsic properties independent of its environment. The properties it shows, particle-like or wave-like nature, will depend on the experimental situation, that is, on the apparatus it is forced to interact with in the observation. Therefore, the last sentence, that the particle it shows particle-like or wave-like nature depends on the experimental situation, that takes us to some quantum conclusions, which is quite different from the mechanistic way of looking at the reality of matter, which would say that there is no objective world independent of the observer. All that really out there is raw, unformed data waiting to be interpreted by you, the perceiver. On the other hand, the observations done by quantum physicists, the laws of physics can be formulated only in terms of probabilities, and it becomes more and more difficult to separate any part of the universe from the whole. Thus, at subatomic level, matter does not exist with certainty at definite places, but rather shows tendencies to exist. And atomic events do not occur with certainty at definite times and in definite ways, but rather show tendencies to occur. In quantum theory, individual events do not always have a well-defined cause. For example, the jump of an electron from one atomic orbit to another, or the disintegration of a subatomic particle, may occur spontaneously without a single event causing it. We can never predict, in that sense, when and how such a phenomenon is going to happen. What we can predict, or what at most we can say about this phenomenon, is that about its probability. This does not mean that atomic events occur in completely arbitrary fashion. It means only that they are not brought about local causes. The behavior of any part is determined by its non-local connections to the whole. And since we do not know these connections precisely, we have to reconsider the philosophical notion of cause and effect. Perhaps we need to replace this notion by the wider concept of statistical causality. It was Heisenberg's achievement to express limitations of the classical physics in a precise mathematical form, which is known as the uncertainty principle. It consists of a set of concepts, a concept that can be applied to atomic phenomena. These relations take out the limits of human imagination in the atomic world. That is to say, whenever we use classical terms, particle, wave, position, velocity, to describe atomic phenomena, we find that there are pairs of concepts or aspects which are interrelated and cannot be defined simultaneously in a precise way. The more we emphasize one aspect in our description, the more the other aspect becomes uncertain. And the precise relation between the two is given by the uncertainty principle by Heisenberg. So, quantum physics faces us with a quite different world. This one is not exactly as our senses picture it. In contrast with the mechanistic view of the world, the new worldview emerging from the new physics can be characterized by words like organic, holistic, and systemic. Thus, the universe is no longer seen as a machine made up of multitude of objects, but has to be considered like a totality, a dynamic whole whose parts are essentially interrelated and can be understood only as patterns of cosmic organism. So from that perspective, what are we to say about matter? Matter exactly different from that of the mechanistic conception. The core of the matter, from what we have observed from the quantum physics, is something different. If we ask about the ultimate readout of the physical world, we will get a very different answer than the one we could expect following the classical physics. It's an answer quite different from the classical way of looking at things. As we penetrate into matter, nature does not show us any isolated basic building blocks like atoms, but rather appears as a complicated web of relations between the various parts of an ununified whole. Thus, according to Heisenberg, the world thus appears as a complicated tissue of events in which connections of different kinds alternate or overlap or combine and thereby determine the texture of the whole universe. Thus, we understand that the picture of the universe from the sense of matter, the core of the matter as we understand from quantum physics, is quite different from that of the mechanistic conception of matter and the conception of the universe. And perhaps it may go very well with the matter form theory of Aristotle in order to know the essence of matter. The essence of matter is not of any particular building block called atoms, but rather it is the relations of form and matter. Thus, the new world given by quantum physics seems to be more in line with our philosophical conception of matter form theory of the world. So today we stop our class, and tomorrow we will see the new topic on space. Thank you.